In this video, we're going to look at parametric equations for vectors, and we're going to see how they can be used to determine the coordinates of a point that sits on a line. Just before we do that, I just want to introduce our three unit vectors, I, j, and k. Now, essentially, all a unit vector is a vector that has a magnitude of 1 in a given direction. So if we look at the I vector first of all, it has a magnitude of 1. Its column vector is 1, 0, 0. Therefore, it's in the direction of the x-axis with a length of 1. So we can add it to our sketch here. This represents the unit vector I. Second, we have the unit vector j with the column vector 0, 1, 0. That means it doesn't have an x or z component, it has a y component, and that y component has a magnitude of 1. So again, we can add that to our sketch. J is this vector here. Now finally, we have the unit vector k, the column vector 0, 0, 1. It has no x or y component, but it has a z component equal to 1. So here is our vector k. Now the reason these are important is that we can use this as an alternative way of defining a direction vector. And I'll give you a quick example. Let's say, for example, we had the direction vector d, and it was 3i minus 2j plus 2k. Well, we've seen how we multiply a vector by a scalar. So what we would actually have here is we would have 3 times the unit vector I of 1, 0, 0 minus 2 times the unit vector j of 0, 1, 0 and plus 2 times the unit vector k of 0, 0, 1. So our next step is to multiply each of those components by the scalars. So our first vector would become 3, 0, 0, or 3 times the x component of 1, minus 2 times 0, 1, 0, which would give us minus 0, 2, 0, and plus 2 times our final vector of 0, 0, 1, which is just 0, 0, 2. Now we can combine all of that and our final vector, adding all of our x components. We've got 3 minus 0 plus 0, which is just 3. Our y components are 0 minus 2 plus 0. And our z components are 0 minus 0 plus 2. Therefore, our final vector is just 3 minus 2, 2. Now, if we compare that to the original direction vector, we can see 3i, or 3 in the x direction, minus 2j, or minus 2 in the y direction, plus 2k, or plus 2 in the z direction. So in actual fact, to jump directly from this to this is very straightforward. So it just provides us with an alternative means of notation. So next we can begin to introduce parametric equations, which are used to determine when points sit on lines. And in the top right hand corner we've got a diagram. We have a line and we have a point A which sits on that line. Point A has the coordinates minus 1, 4, 2. Now in order to define a line, we need to know two things. We need to know the coordinates of a point on the line, and we also need to know the direction of the line. So we need to know the coordinates of the point A, but we also need to know the direction of that line, or the direction that that line is travelling in. And so our direction vector in this case, we're going to define in the following way. We're going to say that it's 2i minus j plus 3k. So now we have a point on the line, and we also have the direction of our line. What we're going to do next is we're going to find the coordinates of another point that sits on the line, and this point we're going to call point B. And the only thing that we know about point B is that its x component is 3. So we don't yet know its y component, and we don't yet know its z component. We're going to need to find those. So let's set up an equation, and our equation states that the position vector for B, OB, equals the position vector of A, OA, plus our direction vector times a parameter that we're going to call t. So this term here represents our point on the line, d represents the direction of our line, and this parameter t is basically a multiplier. It basically tells us that any multiple of the direction, when added to point A, will give us a second point on the line. So just to explain that a bit more, we know that OA represents the position vector of point A, and D represents the direction of the line. Now, any multiple of t, let's say for example t was 1, that would give us a point on the line. If t was 2, that would give us another point on the line, and so on. So t is just a multiplier, or our parameter. Now we can use this equation to find out some more information about the vector OB. But let's rewrite this in a slightly different form, because the vector OB in effect is going to have an x, y and z coordinate. So let's rewrite that as x, y, z. They're the things we're trying to find. We're trying to find the coordinates of point B. OA we can write as a column vector, so instead of -1, 4, 2 as coordinates, we can write it as -1, 4, 2, the column vector. And instead of writing the direction vector as 2i minus j plus 3k, we can separate that into a column vector. 2i represents 2 in the x direction. Minus j represents -1 in the j direction. Minus j is just the same as -1j. And 3k, k is our z direction, so 3 can go at the bottom of the column vector. And that's being multiplied by t. Now in effect, t is just a scalar. We can split this into 3 separate equations now, because we have an equation for x, and the equation for x using our top line here states that x equals -1 plus 2t. So x equals -1 plus 2t. We can write a second equation for y using the second row from each of our vectors, and we have y equals 4 plus -1t, which is just -t. And we have z equals 2 plus 3t using the bottom row of each of our column vectors. Now, if we refer back to what we know about point B, the only thing we know about point B is that its x-coordinate is 3. So if we take the first of those parametric equations, we know here that 3 equals -1 plus 2t. And now we can find the value of our parameter t using that equation. First of all, we need to add 1 to each side to isolate the term 2t, and we get 4 equals 2t. And next we divide each side by 2, and therefore we know that t equals 4 over 2, which is just 2. We now know the value of t that defines our point B. So now we can find our y-coordinate, because our y-coordinate is just 4 minus t, so y equals 4 minus t. Well, we've just said that t is 2 for point B, so our y-coordinate is 2. And finally, we can do that for our z component. We have 2 plus 3t, z equals 2 plus 3t, well t is 2. 2 plus 3 times 2, or 2 plus 6, is just 8. So z equals 8. So we can replace the 2 question marks for the y and z coordinates of our point B, and we're going to replace them with 2 and 8. So point B has the coordinates 3, 2 and 8. So let's determine the vector AB, and then we can find the distance between the points A and B. So as we've seen in an earlier tutorial, the vector AB is the vector OB minus the vector OA. Our vector OB we now know is 3, 2, 8. And our vector OA is -1, 4, 2. Therefore, our vector AB is 3 minus minus 1, which is 4. 2 minus 4 is minus 2. And 8 minus 2 is 6. And finally then, the magnitude of AB, or the distance between the points A and B on the line, is the square root of 4 squared plus minus 2 squared plus 6 squared. That's the magnitude of the vector here. That's the same as the square root of 16 plus 4 plus 36, which is the same as the square root of 56. And that gives us an answer of 7.483. So in this tutorial, we've used the equation of a line in vector form to find the coordinates of a second point on the line, point B. We've then used that to find the vector AB, and we've finished by finding the distance between A and B, which is the same as the magnitude of the vector AB. And the distance between points A and B in this case was 7.483.